Now the third case is when you've got even powers on both sine x and cosine x. So m and n are even when you're doing integrating products of powers. So in this case, what you want to do, your strategy is to reduce your powers on sine x and cosine x using the following identities. So these are the half angle identities for sine and cosine, and then this is the double angle identity for sine. So let's look at an example, see how we can put these to use. So we want to do the integral from 0 to 2 pi of sine to the 6th x dx. So even power on sine, and then power on cosine is 0, which is also even. So even powers on both. So what we want to do here is we first want to take that sine to the 6th, and we want to write it as 0 to 2 pi, and this will be sine squared of x cubed dx. And then our sine squared x right here, the half angle identity, we're going to plug that in. So this is integral from 0 to 2 pi, and on the inside of those parentheses, 1/2 times 1 minus cosine of 2x. That gets cubed dx. So now we want to cube each piece here. So if we cube the 1/2, we'll get 1/8. Let's bring that out in front of the integral. And then we got integral 0 to 2 pi. And now we want to cube this 1 minus cosine 2x. So let's go ahead and work that out separately, and then we'll plug it in here. So we want to compute 1 minus cosine of 2x, and that whole thing gets cubed. And so we need to use binomial theorem to do this. Or Pascal's triangle if you want. So remember, Pascal's triangle starts with a 1, we've got 1's on the side. You always start with 1's on the side, and then you add the numbers in the middle to get the next entry below. So 1 and 1 is 2. 1's on the side here. And then 1 and 2 is 3. And a 2 and 1 here is 3. So this is a plus b to the 0, first, second, and third. So these are the coefficients for cubing. So our coefficients are going to be 1, 3, 3, and 1. And then we take powers of 1. We'll start at third power and go down. So 1 cubed times 1 squared times 1 to the first, and then no factor of 1. And these are all pluses, by the way. And then powers of cosine 2x will start at 0 and go up. So no factors of cosine 2x there. And then we'll have 1 factor of cosine 2x in the next term. And then we'll have 2 factors here. Get Pascal out of the way. So this will be a cosine squared 2x, and then 3 factors here. So this will be a cosine cubed 2x. So let's go ahead and transfer this up. So we are integrating 1 in the first term, 3 cosine 2x, 3 cosine squared 2x, and then cosine cubed 2x. And dx. And now we want to break this up and take the integral of each of the 4 pieces. This looks like a lot of work, doesn't it? It is. So integral 0 to 2 pi of 1 dx plus the 3 will factor out of the integral. and then integral 0 to 2 pi of the cosine 2x there, dx, plus the integral of this term. We'll factor the 3 out in front. Integral 0 to 2 pi cosine squared 2x dx, and then integral of the last term, 0 to 2 pi cosine cubed 2x dx. Close our parentheses. That whole thing gets multiplied by 1/8. So now we just have to evaluate these smaller pieces. So this first integral, that one's easy. So we can do that. We got a 1/8 out in front. This first one, antiderivative of 1 is just x. That gets evaluated from 0 to 2 pi. And then this one, cosine of 2x, if we go ahead and graph that on the calculator. So we want cosine 2x, we'll close parentheses, graph. And you can see that looks like a regular cosine curve. We're doing 0 to 2 pi, so let's go to our window. For our x min, let's do 0. For our x max, let's do 2 pi, so 2, and then it's second functional caret, second caret, so 2 pi there. And our x scale, we can go ahead and leave that at 1. For y min, why don't we do -1 and y max +1, because those graphs only go from 1 to -1. And let's go ahead and graph. So that's our graph on 0 to 2 pi of cosine 2x. And what you see here is that we will have, this is a definite integral. Definite integral is signed area. Well, this area will cancel out this one, and then these two positive areas will cancel out this negative area. So that's actually going to be 0. So this is actually going to be 0. And again, the reason is we graph that. There's x-axis, y-axis. This is 1, -1. This is 2 pi. And it does 2 complete cycles. And we got positive area here and negative area there, and the areas cancel. And that's because we've got a function that is symmetric with respect to the y-axis, and then we've got this complete interval 0 to 2 pi that captures full cycles, 2 full cycles. So that part's easy. Let's go ahead and bring this one down. And so then we've got a +0, so that drops out. And then this one, cosine squared of 2x, we're going to use that identity again. So cosine squared of x, 1/2 1 plus cosine 2x. So if there were a 2x here, then this will double and be 4x. So whatever this angle is, this one doubles it. So for that cosine squared 2x, we're going to trade that out. We've got a 3 out in front. And then this will be integral 0 to 2 pi, 1/2, 1 plus cosine of 4x dx. And then this integral on the end, the cosine 2x has 2 complete cycles in there. The cubing, that does change the shape of the graph a little bit, but it still has symmetry. Let's check that out. So on the calculator, go back to our y equal, and I just want to put a cube in there. I'm going to go here, and I'm going to do a second insert. Let's see, second insert. Well, maybe it won't let me do it. So let's go ahead. Oh, I know. Yeah. Let's see, 2x, close my parentheses. I need to put parentheses around this whole thing. So it's going to be second insert a parenthesis, go out on the end. Whoop, didn't insert my parenthesis. There we go. And out on the end, close parenthesis, that whole thing cubed. That's how we have to do our cube. And let's go ahead and graph on that interval 0 to 2 pi. And looky here, this positive area will cancel this negative one out, and then these two positive areas cancel this negative. So again, that integral is going to be 0. Okay, that's helpful. So this one is also going to be 0. And that's because we've got a even function on a symmetric interval. So this comes down, levels out for a while, and let's see here. And again, we got our plus, 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 which is canceled by minus, minus. So that's a 0 on the end. So really, we've got our plugins in there, 2 pi minus 0, which is just 2 pi, and then we've got to evaluate that integral. The 1/2 can come on the outside here, so we are getting closer to being done. This was not as bad as we thought at first. 2 pi minus 0 is 2 pi, plus 1/2 comes out with a 3 halves. And now we're ready to integrate here. Antiderivative of 1 is x. Antiderivative of cosine 4x is going to be sine 4x. And instead of multiplying by 4, we're going to divide. So 1/4 sine 4x. And then that gets evaluated from 0 to 2 pi. It's got a 1/8 on the outside, 2 pi, and plus, let's see, plug in a 2 pi there. We're going to have 2 pi plus 1/4 sine of 2 pi times 4, 8 pi. And then minus, if we plug in a 0, we get a 0 there. And here we get sine of 0, which is 0. So both those pieces will be 0. And then sine of 8 pi here, that's 4 complete revolutions. And y-coordinate on the unit circle is 0. So that term drops out as a 0. So we really just got 2 pi plus 2 pi, 4 pi. Oh, let's see, forgot our 3/2. Almost. So let's see, 2's would cancel there. 2 pi plus 3 pi, 5 pi. So you got a 1/8 on the outside, 5 pi. So this is 5/8 pi. So, and you can double check that on your calculator, but if you look at the unit circle, we've got 0 here, 1 revolution, 2 pi, 4 pi, 6 pi, 8 pi, ends you at the point 1 comma 0. 1 is cosine 8 pi, 0 is sine of 8 pi. So that was, this is 0 right here. So 5/8 pi for a final answer. Whew, that's an accomplishment. Pat yourself on the back for that one.